Alright, where are we? In the first episode of this series on mechanics, we introduced mechanical quantities, or mass-carrying quantities, combining the dimensions of mass, space, and time. The most well-known examples have space and time exponent x and y that are small integers, which is quite convenient since we can represent them in a table, a map of the explorations of mechanics since the Renaissance. No matter which one we pick, the choice of a single mechanical quantity is powerless. But when considered in pairs, mechanical quantities can be used to rationalize sizes, durations, and motions of all sorts. When these motions are expressed as some types of length scale evolving over time, the formula is pretty simple. The variable size d is a power law of the variable time t, and the exponent is directly given by the relative dimensions of the two underlying mechanical quantities, q1 and q2. And so the exponent just depends on the number of lines and columns separating the two quantities. The quantity on the right, q1, impels motion. It drives motion. The quantity on the left impedes the same motion. Pairs are the elementary building blocks of the relationship between mechanics and kinematics. To each pair corresponds a kinematic power law. We've learned a lot from pairs. We talked about them for 8 episodes, and it is now time to address trios of mechanical quantities. Two cases must be distinguished, whether the three quantities are aligned or not. We'll discuss the non-aligned case first. This will occupy us for a few episodes. We'll come to the aligned case later in the series. When we consider a pair, say energy and density, we get a power law. In this case, Taylor scaling for the dynamics of detonations. Evidently, this mechanical model is quite successful at explaining the kinematics of the front of this specific explosion, Trinity, the first nuclear test. At least for the time range represented here, from around 0.3 milliseconds to 0.1 second. Should we expect this power law to extend indefinitely? Of course not. That would be absurd. If extended indefinitely in the future, this explosion would end up engulfing the whole Earth. And if extended in the past to the instant of detonation, this scaling would lead to all sorts of divergent behaviors, the front speed, for instance, blowing up to infinity. At some points, before and after, other mechanical quantities will start to play a role, and the trajectory of the front will change its path. Let's say a crossover like this happened before Taylor's regime. Evidently, the point of intersection has remarkable coordinates. It is the only point belonging to both lines. It happens at a particular explosion radius and at a particular time. What we will see in this 9th episode is that in any event, like this one, three mechanical quantities are at play. These events provide transitions between different regimes. They are turning points, where the impelling and impeding factors are changing. Moreover, these events provide a way to define truly objective units, regardless of the perspective, to replace meters, seconds, and any other subjective combinations of these arbitrary standards. These objective units are not set by any standard, but by the phenomena itself. We'll start again with Trinity. Taylor's 2/5 scaling concerns the early dynamics of nuclear explosions, before the mushroom cloud forms. For Trinity, the balance of energy and density is valid from around 100 milliseconds to slightly before 1 millisecond after detonation. If we focus on even shorter times, the trajectory of the front starts to deviate from Taylor's model. Why? Because in this range, the mass of the bomb has a non-negligible effect. For early detonations, we need to consider the effect of the energy E of the bomb, the density ρ of the ambient medium, but also the so-called ejected mass m. So we have a trio of mechanical quantities. We do not know yet what to expect from the combination of three quantities on this table, but what we know is that three pairs can be found in this trio: the energy and density pair, the energy and mass pair, and the density and mass pair. We've encountered these three pairs before. The first corresponds to Taylor's regime. We've been talking about it since episode 5. The second one is connected to the simple speed built by combining a mass and an energy. We talked about it in episode 4. The third one we discussed in episode 2 on simple length. If we re-examine the data from Trinity, we see that Taylor's 2/5 scaling does not capture the earliest data points, which is to say that the balance between energy and density does not govern the earliest dynamics of this detonation. Initially, the energy of the explosion is not phased by the density of the swept-up air, but by the ejected mass of the bomb and of the cabin around it. All that mass adds up to around 8 tons, 7 to 9 depending on how much of the bomb cap we take into account. Combining this mass with the energy of the bomb, we get a simple speed, where the energy is naturally impelling motion and the mass is impeding it. It is an inertial mass. For Trinity, the energy of the explosion was around 21 kilotons of TNT, which is around 8.4 10 to the 13 joules. And the mass was around 8 tons, so 8,000 kilograms. From these two numbers, we obtain a speed around 100 kilometers per second. What is this speed? Going back to the data, we can plot the regime at constant speed, built by pairing energy and mass. The thickness of this purple line reflects the uncertainty on the ejected mass. So it seems that, initially, the explosion front does not follow Taylor's regime, but advances at a constant speed set by the balance between energy and mass. After the two regimes intersect, the speed starts to decrease, and the front follows Taylor's regime. The two successive regimes are impelled by the energy of the explosion, E, but initially the impeding factor is the ejected mass m, and it later becomes the density of the ambient air, ρ. Why is that? What is going on at this intersection that would justify this change in impairing factor? To answer this question, let's compute the coordinates of the point of intersection. Let's call them L and tau. For the Trinity explosion, L is around 20 meters, and tau is around 0.18 milliseconds. To understand these values, we have to connect L and tau to the mechanical quantities at play at this intersection. Easy. We just have to equate the two regimes. We can then solve for tau and L to express them solely from the mechanical quantities. These formulas can also be obtained directly from dimensional analysis. Take the time, for instance. Let's assume that this timescale depends on the energy, the mass, and the density, with unknown exponents alpha, beta, and gamma. The dimensions on both sides must match, and we know how this works. We group the dimensions together, then the exponents of the mass, length, and time dimensions must match, allowing us to obtain the values of alpha, beta, and gamma. We then know how the time tau depends on the energy, the mass, and the density. It is crucial to realize that this timescale is the only timescale depending solely on energy, mass, and density. When we will want or need to stress this property, we will add indices, recalling the underlying mechanical quantities. And as usual, the order of these indices does not matter. This equality is as strict as it gets since it is a definition. The actual time of the point of intersection is only approximately equal to this combination of mechanical quantities, because the regimes may include numerical factors of order 1. We'll come back to this in due time. Now, for the length, the procedure is exactly the same. We have new exponents, alpha, beta, and gamma, and the dimensions give us their values. Here, the length L turns out to be independent of the energy E. It can be expressed solely from the ratio between the mass and the density. So the critical size of the explosion above which the front starts to decelerate is actually a simple length, as defined in episode 2. The length built from E, M, and ρ is the same as the length built from M and ρ. The size of the intersection of the first two regimes is actually a third regime. As discussed in episode 2 of this series, and in the 5th episode of the explosion series, it is the size over which the mass of swept-up air becomes greater than the ejected mass. So the dominant inertia switches from being due to the ejected debris to being due to the air pushed away by the blast front. the three regimes included in the trio intersect at a single event. Previously, we got the coordinates of this intersection by equating the energy mass and energy density regimes. You can check for yourself that equating the mass density regime with the energy density regime or with the energy mass regime would give the exact same coordinates. As long as the three mechanical quantities of a trio form a triangle in the mechanical plane, that is, as long as they are not aligned, then the three associated regimes intersect at a single point, a special event, a turning point of the dynamics. There is no need to give a general demonstration here. Discussing additional examples seems more engaging. With each new example, we'll try to further explore the great impact that these events can have, not just on the dynamics themselves, but on the ways to perceive these dynamics. Let's leave explosions here for now and turn to a different kind of physics, the pinching of liquids. In the past episodes, we've encountered this situation multiple times and discussed two cases in detail, distinguished by the prevalence of viscosity or density. In fact, if we follow the pinching with sufficient resolution, we can see that these influences succeed one another. For every drop comes a time when surface tension, density, and viscosity combine. One drop at a time, studying this new kind of event can tell us how trios of mechanical quantities shape the kinematic plane. When a water droplet pinches off, we've seen that the radius of the neck follows a power law, where the time t is the duration before pinch-off, and so time goes from right to left. The slope is 2/3, and can be understood as a consequence of pairing two mechanical quantities, surface tension and density. Surface tension impels motion, and density impedes it. Will this regime extend forever? Of course not. Some other mechanical factor will start to play a role at some point or another. This regime has been observed in pinching droplets of many kinds, but also for the dual of droplets, bubbles, as in this example where a bubble rises in a fluid and the radius of the neck is tracked over time. Same regime combining surface tension and density, except that here the density is that of the outer fluid rather than the inner one. Let's zoom out to accommodate more data. Here the outer fluid is a silicon oil, keeping the same setup but using a water glycerol mixture for the outer fluid. The pinching of the bubble evidently follows a different scaling law. Here the radius of the neck scales linearly with the duration before pinch-off. This is a regime we've seen before, combining surface tension and viscosity, not density. So why are the dynamics different in these two fluids? How can we know what to expect? An inertial capillary regime or a viscocapillary regime? Additional experiments can help us better understand what is going on here. In this run here, the outer fluid is a different silicon oil, and the pinching dynamics follow a succession of two regimes. Close to the pinch-off points, the radius grows linearly according to the viscocapillary regime. Further away, the radius follows the balance of surface tension and density. The impelling factor remains the same, surface tension, but the impeding factor switches from viscosity to density. The silicon oil has a density, a surface tension, and a viscosity. And all three mechanical quantities are required to understand this event, this crossover. Just as in the explosion case, the coordinates of the point of intersection, the event, can be expressed directly from the three mechanical parameters. They are direct consequence of dimensional analysis. We, the authors of this channel, are attached to this particular event because it was its study that helped us forge the concepts developed in this episode, and more broadly in this series. We've come to call it the Ohnesorge event, the unsorg point, after Wolfgang von Ohnesorge, who was among the first to derive these coordinates. We have some emotional bias toward this particular event, so we gave it a name, but there are thousands of events out there, and naming them all after scientists will not be practical. Keep it simple. This event is just the manifestation in the kinematic plane of the trio of underlying mechanical quantities. In this example, both the size and time associated with this point depend on the three mechanical quantities, because the third regime is neither a simple length nor a simple time. No pair from this trio have their elements on the same line or column. The pair of viscosity and surface tension gives the linear scaling. The pair of density and surface tension gives the 2/3 regime. And the last pair, density and viscosity, one line and two columns apart, this gives a diffusive regime, which we've seen before in the context of boundary layers. Where would this regime be? Going through the same event as the first two regimes, with a slope of 1/2, and a prefactor given by the ratio of viscosity and density, which is also called the kinematic viscosity. So the coordinates of the point of intersection can be obtained from the overlap of the viscocapillary and inertial capillary regime, but also from the overlap of the boundary layer regime, that is the visco-inertial regime, and the viscocapillary regime, or inertial capillary regime. At this event, the effect of viscosity, density, and surface tension meet. Regimes, lines, are the results of the interplay of pairs of mechanical quantities. Events, points, are where trios connect. Why aren't there any data points on the visco-inertial regime? Well, the neck does not follow this trend, but if we were to look more closely at the flow in and around the neck, we would see that close to pinch-off, the strain region or boundary layer extends beyond the neck size, whereas when the neck is larger than the crossover size, the strain region is smaller than the neck. We'll have the opportunity to come back on this in the droplet series that we are preparing. The important for now is to see once more that three mechanical quantities give three regimes intersecting at a special event with coordinates obtained directly from the mechanical quantities. For this experiment, the value of density, surface tension, and viscosity give a point with a size around 50 microns, 80 microseconds before pinch-off. If we consider a fluid with different properties, the values will change accordingly. The greater the viscosity, the larger the size, and the longer the time. The greater the density or surface tension, the smaller the size and shorter the time. In the two fluids that we initially considered, the experiment could only feature one regime, the inertial capillary regime for the silicon oil, and the viscocapillary regime for the water-glycerol mixture. Why only one regime? Because in these two cases, the intersection, the event where dynamics change, falls outside the experimental range. For the blue curve, it must have happened before. For the green curve, it must have happened after. If we zoom out, we can actually see where these points would have been expected according to the formulas. Although the two curves correspond to neck radii of almost the same sizes, and the dynamics were captured over a similar time range, the differences in the mechanical properties of these two fluids are such that what we are seeing is very different. The blue data points correspond to the late inertial dynamics, once the special point has been crossed, whereas the green data points are still displaying the early viscous regime, before the event. The meter and the second are convenient standards to measure space and time, but they are completely arbitrary. 1 second and 1 meter are not experienced in the same way by these two fluids here. These extrinsic and subjective units do not take into account the mechanical trio underlying the dynamics. In contrast, for each fluid, the coordinates of the event provide intrinsic and objective units of space and time. If we want to better appreciate the similarity between these dynamics, we should be measuring lengths and durations with respect to the standards provided by the mechanics of these motions. If we don't, multiplying experiments will only bring about more confusion. Let's watch this confusion build up. So far we've talked about the trio of surface tension, density, and viscosity in the context of pinching, but these regimes have also been observed in other configurations, as in the spreading of droplets on substrates. In this case, the size is the radius of contact, and the time runs from left to right. Viscocapillary and inertial capillary regimes have also been seen during coalescence, while the size is the radius of contact. The precise geometry of the coalescence does not seem to matter too much. Similar dynamics are also observed for pinching soap films, for liquid bridges between two plates, pen and drops, and as we saw, pinching bubbles. When the fluids are identical, the curves generally overlap well. For instance, this curve comes from a soap film, and another study on a similar soap film finds the same dynamics. Same fluids overlap, but the curves from different fluids crisscross each other in a tremendous mess. There are 37 curves from 13 different studies of spreading, coalescence, and pinching on this plot, which we compiled in a recent review. Sizes range from nanometers to centimeters and time from nanoseconds to hours. Using these subjective units, the meter and the second, or any other subjective standards, it is very hard to see that all these dynamics essentially belong to the same category. They are all due to the interplay of surface tension, density, and viscosity. For each experiment, these mechanical parameters are constant, and we can combine these constants to obtain the coordinates of the special event at the intersection of the regimes, and use these coordinates as our units. When we do, all curves align neatly. The data points here are exactly the same as in this big mess, but for each fluid, we've constructed units based on the mechanics and not on our international, national, or personal preferences. Units based on mechanics. In blue, the 2/3 power law is the inertial capillary regime. In green, the linear trend is the visco-capillary regime. And if need be, we can also represent the visco-inertial regime, capturing the dynamics of boundary layers, which are not tracked in these experiments. Note that to reach such a satisfying overlap, the actual units, L and tau, must take into account the dimensionless prefactors of each regime, the deltas we talked about a few times in the past episodes. We'll come back to this subtlety later in the series, and you can check the supplementary of our recent review if you are impatient. For now, we'll just keep in mind that these corrections are absorbed by the approximate equality signs here. When we use these objective units, the point of intersection happens for a time of 1 and a size of 1 by construction. In these units, the regimes can also be expressed in simplified forms. For instance, the scale size of the viscosity and density regime is just given by the square root of the scale time. Some people are even bold enough to write this simply as d equals t1/2, while the objective units are assumed implicitly. To avoid confusion with the original time and size given in subjective units, some add a tilde or some similar reminder that the units have been changed. We will be even more cautious and systematically write down the ratios. These ratios and the definitions of the units can be used to check that this formula is indeed the same as the one we started with. We just have to express the units L and tau from their mechanical factors. The surface tension disappears and the viscosity and density indeed compile to form the kinematic viscosity. So in this objective system of units, the boundary layer regime is just a square root, and you can verify for yourself that the inertial capillary and visco-capillary regimes are also simple power laws. When dynamics are governed by the interplay of surface tension, viscosity, and density, these objective units are much more judicious than anything else we could have chosen. The dynamics of very different fluids overlap nicely, and the formulas for the regimes conveniently simplify. Of course, we are free to use conventional units, arbitrary standards set for all, independently of the mechanical properties of the fluid. But what we get is messy. This mess is not due to the inherent complexity of the physics at play, but to the reference frame we've imposed. Once we align our units with the mechanics, things clarify greatly. The consequences of this change of attitude are far-reaching and could be further explored on this particular example. But let's investigate a different context to stress how general these consequences are. Let's talk about waves and ripples, which we introduced in episode 7. We will assume that the fluids under study are not too viscous, so we can solely consider the effects of surface tension gamma, density rho, and the weight density psi. We have 3 mechanical quantities, so we have 3 regimes, here expressed as a size evolving over time. Since surface tension and force density are on the same line, the last regime is actually a simple length. It is the capillary length from episode 2. Below this length scale, droplets do not significantly feel the effect of gravity. The second regime we've seen on a few occasions already, and the first regime we just talked about it. As we now know, in the context of waves, it is often more practical to express the regimes from the perspective of a frequency versus a wave number, that is, as dispersion relations. In episode 7, we gave one example, the dispersion relation of capillary ripples on the surface of water. Here, the frequency is proportional to the wave number to the power of 3/2. The dynamics are due to the struggle between surface tension and density. Now, if we plot the long wavelength seen on the surface of lakes or oceans, we get a different power law. The frequency grows like the square root of the wave number, as expected for the balance of weight density and mass density. Both experiments essentially use the same fluid, water, and the differences in behavior that we see here are due to the relative positions of the experimental range with respect to the point of intersection of the two regimes. The physics are quite different before and after this point is crossed. On either side, the density of the fluid is the impeding factor. But for small wave numbers, that is for large wavelength, the weight density is the impelling factor, whereas it is the surface tension for larger wave numbers, and so shorter wavelengths. If additional data are gathered in the intermediate range, we can see that the frequency switches from being governed by surface tension to being governed by gravity. How smooth this transition is goes beyond our point today. We will talk about it another time. What dimensional analysis tells us right away is that the critical wave number at the transition is given by balancing surface tension and weight density. Neglecting numerical factors of order 1, the critical wave number is the inverse of the capillary length. These 3 lines and their common intersection are the direct consequence of considering the trio of surface tension, density, and force density. Just as we did for explosions and droplets, we can compute the coordinates of the point of intersection. Here they are expressed as a critical frequency and wave number, since it's the perspective we've chosen for this plot. We do not have as much data on this trio as we did for the unsolved point, so the rescaling of the curves cannot be displayed in all its glory, but the principle remains the same. For instance, take this additional dataset on capillary ripples in a mixture of water and alcohol. The density of the fluid is not that different from water, but the surface tension is around 60% smaller, so the regimes and their intersection move accordingly. Then, if we use the coordinates of the point of intersection as units of frequency of wave number, the data overlap. Here again, the best overlap requires to take into account the dimensionless prefactors of the regimes, so the actual coordinates include factors of order 1, which are absorbed by the approximate equality, but that we should keep in mind, hence the little asterisks on the units. With these mechanical units, all data points fall on what is sometimes referred to as a master curve, which in this case is the succession of 2 power laws, 1/2 and 3/2. The connection between mechanical trios, events, and objective units is as much true when we use a dispersion relation as when we use a length versus a time, similarly to the 2 previous examples for explosions and droplets. The event associated with a trio is characterized by a length or a wave number, a time or a frequency, and by any other kinematic metric we may choose. For instance, instead of representing the frequency versus the wave number, we can represent the wave speed versus the wave number. The wave speed scales like omega over k, so from this perspective, the capillary regime is a power law with an exponent of 1/2, and the gravity regime has an exponent of -1/2. So there is a minimum speed at the crossover, which can be naturally expressed solely from the mechanical quantities of the trio. Regardless of the perspective, the event remains. So if we like, we can use the wavelength instead of the wave number. Now ripples are on the left and waves on the right. This perspective can help us connect the dots with the last episode, on the right angle for a particular regime. Here, the horizontal axis is the wavelength d, divided by the capillary length. So one way to understand this axis is as giving the value of a dimensionless number. And we've seen this one already. It's the square root of the bond number. We just called it n with the mechanical pair as indices. If we want, we can use the square of the wavelength as the horizontal axis, which in objective units is precisely the simple dimensionless number associated with the force density and surface tension regime. So from this perspective, the horizontal axis is the right angle on the regime built by combining psi and gamma. Can we select a new vertical axis that would provide a right angle too? Yes, we have two choices. On the capillary side, the dimensionless number is the Weber number. On the gravity side, it is the Froude number. If we choose the Weber number for the vertical scale, the inertial capillary regime becomes a horizontal line. And you can check that the gravity regime corresponds to a Weber number growing linearly with the bond number. If instead we choose the Froude number as the vertical axis, then the inertial capillary regime corresponds to a Froude scaling as the inverse of the bond number. For the sake of completeness, we can also represent the Froude number versus the Weber number. Now the capillary and gravity regimes are naturally vertical and horizontal, and the regime combining force density and surface tension is diagonal. When we consider a trio of mechanical quantities with an associated event, there is no perspective we can choose that is the right angle for all regimes. There is always one regime which is diagonal, and which can be expressed as some equation between the dimensionless numbers of the two other regimes. As we saw in episode 8, the regime associated with two mechanical quantities, here surface tension and force density, is by construction given by the dynamics such that the dimensionless number of this regime is of order 1. Now, a third mechanical quantity, density here, allows to express this regime from the two other dimensionless numbers of the trio. And the same is true for the inertial capillary regime and gravity regime. You can easily check that these three equivalences are related by this identity, connecting all three dimensionless numbers. Given how the mechanical quantities are placed in the table, this identity is no mystery. It just says that you can go from surface tension to density directly or by first going through force density. These three perspectives are nice if you're into simple dimensionless numbers. We'll see later how they can be used to further our understanding of the kinematic plane. But they are not much more legitimate than other perspectives, like the wave speed versus the wavelength we used before. The vertical axis of this plot is not a simple dimensionless number, but it is a dimensionless number anyway. The ratio of the speed and the speed at the intersection. It depends on three rather than two mechanical quantities. So this axis is actually a mixture of the simple dimensionless numbers, as we can show now with a few lines of algebra. Simple dimensionless numbers are constructed so as to be linear in the mechanical quantities, so we can factor out the power 1/4. Now we have multiple choices depending on which dimensionless numbers we want to reveal. Say the Weber and Froude numbers. The scaled wave speed can then be given as the product of the Weber and Froude raised to the power 1/4. We'll leave it as an exercise for you to check that the dimensionless speed can also be given from the Bond and Froude, or from the Weber and Bond. So the properly scaled speed can be expressed from any pair of simple dimensionless numbers. This kind of decomposition into simple factors is here done for the speed, but it could be carried out for any choice of kinematic variable. All this may sound arcane, but it's really basic algebra, bound by the identity of the trio. Thanks for sticking out through these calculations. We felt we had to do them explicitly once, we won't go through so much trouble for the rest of the episode. All these formulas for the regimes and their intersection are direct consequences of the dimensions of the mechanical quantities of the trio. When we dealt solely with pairs, we bothered to give a general formula for the regime in the canonical perspective, that is, as a length versus a time. This formula is simple enough to be useful. Now that we are dealing with trios, we could give explicit formulas for the coordinates of the point of intersection in terms of q1, q2, q3, and their dimensions, x1, x2, x3, y1, y2, and y3. You're welcome to derive them yourself. They are too ugly to be displayed here, too ugly to be of any use. What's useful is to remember the method, the algorithm to go from three mechanical quantities to the intersection, and that method is simple. Let's follow it on one more example, returning to the topic of turbulence, discussed in episode 7. We saw then that the spectrum of inertial turbulence follows a minus 5/3 scaling. But this scaling breaks down above some high enough wave number. And high wave numbers correspond to small sizes. In the context of turbulence, one speaks of Kolmogorov microscales. At the transition, the power density pi and mass density rho of the inertial range combine with the viscosity eta. The three mechanical quantities lead to three pairs associated with three regimes, here given in the canonical perspective. The three mechanical quantities form a triangle in the mechanical plane, so the regimes associated with the three pairs intersect at a single location in the kinematic plane, at what we call an event, a space-time point. When the kinematic plane is seen from the canonical perspective of a length versus a time, the intersection quite directly mirrors the triangle in the mechanical plane. If you enjoy trigonometry, you can check that the angles in the mechanical plane are reflected in the kinematic plane. This is true for this example as much as for any other. So we've got a trio and three associated pairs. The first one corresponds to the turbulent dynamics of train blobs, as discussed in episode 7. The second regime pairs viscosity and density and correspond to the laminar boundary layers. The third regime is a pair we've not seen before, and since viscosity and power density are on the same column, it corresponds to a simple time. The regimes can be translated to any perspective we may choose, and in the case of turbulence we know that power spectra are quite useful. In addition to Kolmogorov minus 5/3 spectrum, we have two additional power laws. Where would they be on this plot? The intersection happens in the vicinity of the departure from Kolmogorov scaling. The intersection does not exactly align with the transition in the data, and again, the dimensionless corrections are to blame. The regimes are not strict equalities. The approximate signs omit dimensionless prefactors of order 1, and these prefactors remain influential in the spectral perspective. In episode 7 we discussed translations formulas to go from the canonical to spectral perspective, but we did not get into the detail. And we omitted possible prefactors of order 1. The 2 pi's here, the 1/2 there, etc. These factors that we can call gammas combine with the deltas of the canonical perspective and produce quite nasty looking corrections to the power spectra. These corrections are responsible for the slight misalignment with the data. The regimes contain corrections, and so would the coordinates of the point of intersection. So we use the little asterisk again to keep in mind that these corrections are hidden behind the approximate equalities. The discovery of this special event, this turning point of the dynamics, is quite universally credited to Kolmogorov. Note that the inverse of the critical wave number is usually called Kolmogorov length and written in terms of the kinematic viscosity, nu, and the specific power, epsilon. So the kinematic prefactors of the density and viscosity regime and power density and density regime. The viscosity and power density regime is left out. In contrast, when the coordinates are written fully mechanically, no regime is excluded nor favored. Just as we did for droplets and waves, we can use these coordinates as objective units to overlap multiple experiments in different configurations. These are the data gathered in the tidal channel we've been focusing on so far. Here are data in wind tunnels, where the fluid is air, 1,000 times less dense than water. Here is an example of turbulence in liquid helium, with vanishingly small viscosity. And here is a turbulent swirling flow of water. All curves are given in international units, and we know by now that these standards are arbitrary, and that we can replace them by the objective units we get from the mechanical parameters. If we use these units, the curves overlap. However, the overlap is not perfect and the crossover is a bit shifted away from the point of coordinates unity. And this is due again to the dimensionless corrections of order 1. If we take them into account, the picture becomes clearer. For small wave numbers, the dynamics follow the minus 5/3 spectrum. Eventually, the regime based on power density and mass density intersects with the dynamics of laminar boundary layers. And through the same intersection, we find the third regime, combining power density and viscosity. Drawing on a seminal 1979 review article by Dean Chapman, we can add more datasets to reach a pretty satisfying overlap of 22 different turbulence experiments on different fluids and different flow configurations. The inertial range governed by power density and mass density is pretty wide, but the viscous range does not seem to follow the -3 power law for long. Why is that? Well, the answer to this question is still debated, and it goes beyond our scope today. But we may get a hint if we represent these dynamics from the canonical perspective. From this perspective, the power density and viscosity regime is a simple time, sometimes called Kolmogorov time. If we recall that the inertial regime is following the size of strain blobs over time, then when the size of the blob is small enough, getting to Kolmogorov's microscales, the scaling would suggest that the size drops to 0 instantaneously. Such discontinuity does not seem possible, and an alternate route is followed. This feature is not unique to the microscales of turbulence, and we will see another time that it actually occurs whenever one of the regimes of the trio is a simple time. Alright. We need to find some kind of conclusion to this video, which is not easy given that this 9th episode is really the introduction to a whole new realm, that of trios of mechanical quantities. Pairs struggle to find a balance, leading to the regimes we are now familiar with. Trios meet at the turning point of the dynamics. A lot of regimes can be built from these standard mechanical quantities alone, and even more events when we consider trios. In this episode, we've discussed early detonations, combining density, energy, and mass, spreading, coalescing, and pitching droplets and bubbles, combining density, surface tension, and viscosity, ripples and waves, combining density, surface tension, and force density, and finally, inertial turbulence, combining density, power density, and viscosity. In these 4 examples, mechanical quantities form a triangle in the mechanical plane, producing 3 regimes intersecting at the same event. The kinematic plane is a reflection of the mechanical plane. The coordinates of the event can then be used as objective units to reveal the mechanical similarities between kinematically disparate datasets. With objective units, dynamics governed by the same mechanics overlap. We've done this explicitly for drops, waves, and turbulence, and you can check the 5th episode of the Explosion series for the crossover in the early dynamics of detonations. In each case, the coordinates of the event are given by the underlying mechanical quantities. Here, the events are shown from the canonical perspective of a length versus a time, but we now know that they can be seen from any kinematic perspective we may choose to adopt. In particular, the variables can be chosen to be simple dimensionless numbers. We've seen this in the case of waves and ripples, but the procedure can be carried out for any event. For each event, the 3 associated dimensionless numbers are connected by an identity. Here again, a direct consequence of dimensional analysis. We'll have the opportunity to encounter many more events in the rest of this series, but you can already explore some on your own. Just pick any trio of mechanical quantities on this table. If they are not aligned, they will lead you there, where they meet, and the partners change when dynamics take a turn and spacetime finds its center. The scientific literature is full of events just like the ones we've discussed in this video, built by combining three mechanical quantities. But there are also a lot of examples that combine mechanical and kinematic parameters, where one of the regime is given in terms of mechanical factors, but not the other one, where we are undecided, afraid to acknowledge the impact of a third player, and missing out on the opportunity that it provides. We'll talk about that in the next episode.